to support all of documents and for my visit. And well, of course, this is my first time in Opava. I like this city, very comfortable for study and to do something in our research topic. Well, it is very clear. So I am here because of my good friend Arman. I met Arman probably 8 years ago at the conference in Kazakhstan. After that day, we keep in touch, become a good friend, and we have the common topics. Thank you, Arman, to introduce me with Dr. Martin. Nowadays, Arman and Martin are my supervisor of my PhD students. So that's why we have the common topics in some kind of research area. So I think it is good experience for me and for my students. I wish we will improve our collaborations in future time. So let me introduce my university and some of research group in our faculty. Maybe it's helpful to find some common topics in this field. So, well, our university is Al-Farabi Kazakh National University, located in the Almaty city. Almaty city is one of the biggest city in Kazakhstan, also the economic capital of Kazakhstan. Well, the Al-Farabi Kazakh National University founded in 1934. Here nowadays 16 faculties and 67 departments or research institute and other technopark. Well, so it is the biggest university in Kazakhstan, almost in Central Asia. Well, total area is more than 100 hectares. Nowadays, they are studying more than 40,000 students, including bachelors, more than 20,000 and 60,000 master students, and more than 6,000 PhD students. So, Al-Farabi Kazakh National University ranked in top 115 in Central Asia. So in our country, it is the biggest and one of the famous university in Kazakhstan. Well, our faculty is reorganized as independent department in 1959 because the oldest faculty was the physics and mathematics. After 1959, it's organized as a faculty of physics. Well, the education process carry out within the departments. Here we have the 4 departments related to the plasma physics, thermal physics, and solid physics, and the last one is Department of Theoretical and Nuclear Physics. I'm working at the Department of Theoretical and Nuclear Physics. Well, the scientific research carried out within the scientific institutes. We have the 3 institutes which related to our faculty. So 2 of them is related to the nanotechnology and engineering. For the theoretical research, we have the Institute of Experimental and Theoretical Physics. Here we have the 4 laboratory which associated to the 4 departments. One of them is Laboratory of General Relativity. Here different kind of research topics which based on the actual problems in research area. One of them is the actual problem of general relativity, gravitation, and quantum thermodynamics. Well, here are some relevant topics listed here, but our research group based on the actual problem of general relativity, gravitation, and cosmology, thermodynamics also. So in our research group, the scientific process based on the research leader or team leaders. They organized a little research group, including the students, master students, and PhD, also young researchers. I listed here some of researchers which related to the actual problems of general relativity. So most of them working on the gravitation, astrophysics, and cosmology. For instance, Professor Takibayev, also he's an academician. His main topic related to the astrophysics, relativistic astrophysics, related to neutron stars, models of neutron stars, the process inside of neutron stars. Well, the second term leader is Jonin Shalif. He's a professor. He has a different scale and research field, as well as dark matter, cosmology, quantum field theory, supersymmetry, and alternative theory of gravity. Also, he was a supervisor of Ablai Khan also. Yeah, the third is Professor Hernando from Mexico. He is our visiting professor, and he was also my scientific supervisor at the PhD course. At our institute, he doing study on the GTD, geometric thermodynamics, also compact object physics. Also, the next is Professor Ivachuk. He is also visiting professor from Russia, Rudain. The main topic is related to the mathematical models of black hole. They unlike black hole also. Well, multidimensional gravity. The next is Professor Abishuf. He is also chairman of our department, head of laboratory in GR. His main topics are related to the motion of extended body in general relativity, nonlinear effect of nonlinear electrodynamics. He also have different research topics related to the nuclear physics, well, reactors. He also the director of medical physics, Institute of Medical Physics. Well, the Professor Penkov also studying on the nuclear astrophysics, electrodynamics, well, etc. The next is Madame Baysen Nurzada. She is now dean of our faculty. So the main topic is related to adiabatic theory of motion in GR. Currently working on the two-body motions, well, here extended two-body motions, stability conditions, etc. The next is Professor Boshkaev Kwantai. Well, he was the PhD of Remo Ruffini. At his PhD, he worked the neutron stars, about neutron stars, white top, the equilibrium conditions of the neutron stars, and the white top taking into account the temperature. Nowadays, he also working on the neutron stars with the combination of the data configurations, as well as the dark matter, halo of dark matter. Well, he was the supervisor of Janirke at the master course. The next is me. My main topic related to the finding the exact solution of Einstein's field equations, compact objects. Well, of course, also related to the motion problems in general relativity. The last one is Aymarat Erlan. He also PhD student. He was the PhD student of Remo Ruffini at Ukrainet. Nowadays, he working on the GRB gamma ray bursts and data analyze, catalog of pulsars. Most of work related to the observation, analyze of observation dates. Well, I listed main topics, a few main topics which I am currently working on because some of pupils working different kind of research area. For instance, some guys working on the well, particles, the fundamental particles, the Bose condensate. Well, also, well, so it's for me it's very unclear. So I just listed my common topics. I can start the last one because the last one is general relativistic effect in the magnetosphere of astrophysical compact objects. This is a new thing for me. We started with Arman, and now I am getting the advice from Dr. Martin. So I think here most of researchers have a good skill in this field. One thing I would like to add, well, it can be investigated also using different configuration of the space-time. Yeah, I last time suggested to the Martin. Well, it is maybe future time. Yeah. The last effect of nonlinear vacuum electrodynamics. Well, this topic, well, it is supported by the Professor Abishov. Well, completely it's well, different thing, but this topic can be split two types. First is theoretical investigation. Second is observation. We'll compare observation with the observation analyze. Well, the last one, Murat Verlan, will realize this observational data, and for the theoretical part, we can split two steps. First is to find the effective configuration of space-time to prove motion equations. Second is related to the computer simulations. So some of guys in our group doing the computer simulations. We hope they can find some well, possible results. And about the first and second, I will explain in the next slide. Well, as I know, the general relativity with very well, to solve the equation of motion in general relativity, it's so hard. Even the cerebral problems in classical mechanics still not well, general solutions. There are not general solutions. Well, it's finally proved by Poincare, but famous mathematicians and physicists focused on this problem. Well, our research group formulated by the academician M. Abdildin. He worked some of analytical approach to investigate the motion problems in general relativity based on the Fox method. Nowadays, we have the first approximation method and second approximation method of Fox. Well, in classical physics and classical mechanics, the particular case of cerebral problem important than the general case, because we know the good example is our solar system. Well, in classical physics, there are a few solutions in limiting in special case. It's like triangular solutions, Euler solutions, and equilibrium points of Lagrange. Well, consider that two main bodies around each other moving in the circular orbits. What could be happen the orbits of the with the orbits of the third body? Well, it is a circular restrict cerebral problems. In general relativity, the motion equations can be found using these two methods. First is Einstein's Infeld-Holtman method, and the second is Fock approximate methods. Using this Fock method, we can prove the motion equations from the Hamiltonian. You can see the Hamiltonian contains, well, classical part and the relativistic part. So in analytically, it is hard to solve, but the stability of orbits can be analyzed using the vector elements of orbits. Well, it's very simple. The average change of vector elements m by the time it can be integrated by the periodic time. The final results presented here, the third equation. In the circular orbits, the orbits of third body is stable. And this is the very simple case. The next step is to consider the quasi-circular orbits. Well, this is the task in the next time. Well, about a second topic. General relativity is the theory of gravity. As a good theory, it should be contain all physical configurations which in gravity involved. In the compact objects, the Einstein's field equations can be split two types. First is related to the vacuum solution. Second is solution with source. Well, in the compact objects, this is easier to consider the axisymmetric space-time. So Zepoy and Wercher investigated the axisymmetric solution of Einstein's field equations, and they proved the field equations as of 6, 7, 8, 9. Well, they found some of special transformation method, and using this transformation method can be generated new solutions from the known solutions. And in the literature, it's called as a delta metric. We know that first exact vacuum solution is found by the Schwarzschild. And next, if you start from the Schwarzschild solution and to apply this Zepoy-Wercher transformations with constant delta, then we can reduce the line element 11. Well, this line element, static vacuum solution of Einstein's field equations. To understanding the additional parameter Q, the properties of parameter Q, we can calculate the invariant George multiples. Well, the lowest multiple moments can be presented as equation 11. Higher multiple moments can be presented a combination of the M0 and the M2. So the M2, this is the quadruple related to the quadruple moment. So in this sense, we called this metric as a Q metric, quadruple metric. And the space-time curvature indicated that some of special properties in this metric. Well, singularity. It is different from the spherical symmetric case. Well, we know that in the Schwarzschild case, 0, 1 is singular points at r equal to 0. And here, very different. Of course, if we know the metric, space-time metric, then we can investigate many things, including the particle motion, well, geodesic motion, well, of course, the shadow also. Well, after that, well, some researchers calculated the shadow using the numerical solutions. Someone calculated the off-equatorial motions, but the final results I presented here. Some part of the results. In the equatorial plane, we can see the quadruple parameter drastically changes the orbits of test particles. Here, compared with the orbits of in the Schwarzschild space-time. Also, in the off-equatorial case, you can see the sum of orbits elevating to the equatorial plane. Well, of course, about metric was in the static case. We would like to investigate the stationary stationary case. Well, there are several methods to generate the static case to the stationary. We started from the Ernst potential. If we know the Ernst potential, we can solve the Ernst equations. After that, one can calculate the stationary metric. The final results are presented in the 17, A Ernst potential. And the stationary metric also the different from the static case and different from the Schwarzschild carry solutions. We calculated all the George invariant George multiple moments and compared with the Kerr multiple moments. Of course, in the limiting case, it is equal to the Kerr multiple moments when Q equal to 0. In general case, the multiple moments presented as equation 21 and 22. So this stationary metric can be described by the 4 parameters: M, rotational parameter alpha, and sigma and Q. Sigma related to the mass of the objects. So all of these solutions can be described the gravitational field of outside of objects. What about interior gravitational field of compact objects? Well, several numerical solutions indicate as to construct a line element in the simple form. The line element 23 is as like the real line element, but we add one more freedom functions as other functions depending on the coordinate r and the theta. So if we consider perfect fluid, well, it is simple model for construct the model of compact objects. Well, the field equations can be presented from the 25 and 29. 30. Well, of course, we have one more equation, 31. It is from the local conservation of energy. The first part equation of 31 is TOF equation, Tolman-Oppenheimer-Volkoff equations. And the second is as like the extended TOF equations. Of course, all of these field equations completely hard to solve because non-linear and second order partial differential equations. To numerical solve, it is strongly depends the initial conditions, boundary conditions. Well, but we investigated the structure of system equations and found some of special properties. And this we found some of special properties as like the symmetry of differential equation systems, and we made the generating method and based on the theorem, which based on the transformation of metric tensors. Let's say thought about differential equations, there are solutions which indexed by 0, 22. Then using the transformations 33 and 34, we can generate new solutions from the given CD solutions. And completely it is different from the CD solutions. Well, detailedly proved this theorem. We can see the application and the application. Well, first of all, we can start from the vacuum case. In the vanishing pressure and the density, this transformation method reduced to the Ziploy-Walker transformation in a vacuum case. If we generate a vacuum Schwarzschild solution, then we can reduce to the Q metric again. And the third case, well, we know there are several solutions, probably more than 129 solutions in the spherical symmetric case. But most of them are unknown in the physical point of view. For instance, they have the negative density, negative pressure. But one of the good example is Schwarzschild perfect fluid solution. Well, it is also the simple model of stars. Well, we generated this Schwarzschild perfectly solutions, and the final results presented in 35 and 37, 36. Yeah, we can see the Schwarzschild solution only radial dependence, and the final results dependence r and theta. So this is completely different from the Schwarzschild solution. Well, the 35 and the 36 is exact solution of Einstein's field equations for the isotropic perfect fluid case. Of course, to make a real good model, we can take into account anisotropy. Well, to understanding the solutions, also, again, we started from the limiting case. Consider that slightly deformed compact objects. For the exterior gravitational field, we can use the approximate exterior solution of Q metric. Well, it's well defined, but for the inside of gravitational field, we linearized this line element as equation 37. Well, we can reduce the field equations. Also, it is hard to solve. But also, we can start from the limiting case when vanishing pressure and density. The field equations can be solved in analytical. Here we found several solutions. Well, the family of solutions in vacuum case. And to understanding the additional parameter Q, the properties of Q, we, using the coordinate transformations, we found Newtonian limiting, and the parameter Q related to the potentials, mass potential to the Newtonian quadrupole parameter. Of course, in general, it is difficult to solve the integral solution of Einstein's field equations. But to close the system of equations, we have to add top equations and the equation of state. We investigated some parts of equation of state, as well as the Chandrasekhar equation of state for white dwarf, and pure degenerate gas model for neutron stars. Well, we showed that the polytropic equation of state is very effective for description of the about field equations. Well, and in particular case, we found regular solutions that pressure and the density regular inside of stars, and satisfy energy conditions, the strong conditions, strong energy conditions, of course. And these solutions can be matched with the exterior solution of Q metric. Of course, for the rotating stars, there are several solutions, starting from Hartle-Thorne formalism, Seydrakian-Shubarian solution, and Fock solutions. In some coordinate transformation, using some of coordinate transformation, we showed that all of these equal to each other. So in the mathematical point of view, they equivalent each other. Well, also in the limiting case, the Hartle-Thorne and the Fock and Seydrakian-Shubarian solutions have a Newtonian limit. Well, in the static case, well, the Q metric has also a Newtonian limit. The next step, we would like to consider equilibrium properties of the fluid inside the stars, as well as the neutron stars and the white dwarf, taking into account the quadrupole parameter. This topic in the process in April, I would like to invite in Almaty, we will hold the international conference, Abdilin readings. So it's part of the conference behind of IPPCT as a participating conference, yeah, on gravitation and cosmology. So these topics are related to my main topics, which current now I am doing. Well, if you have some questions, I will try to answer, and that's all. Thank you, everyone. Yeah. By the way, I listed here some of the pictures from Almaty, near Almaty. Well, the button, middle of the button, it is Almaty city around the mountain, as well as I told before. The mountain, it's very near to a city, center of city, probably 40 minutes, yeah. So some people say that Almaty is Switzerland in Central Asia. Well, so that's all. Thank you very much.